Thank you everyone for attending today's Foxconn Quantum Computing Seminar. Today we have the pleasure of having Andi Gu, who will tell us about constant overhead entanglement distillation via scrambling. So Andi is currently doing PhD in quantum science and engineering at Harvard University. Before going to Harvard, Andi studied at the University of California, Berkeley, with a Bachelor of Arts in Computer Science and Physics. And Andi's research primarily revolves around quantum error correction, quantum information theory, and quantum many-body physics. So Andi, the floor is yours.
Great, thank you for the introduction, and thank you guys for having me. It's a great honor to be giving this talk today, and I'm excited to tell you a bit about our work. So I'm going to be telling you about a paper that we recently put out on constant overhead entanglement distillation via scrambling, and I'm excited to get your guys' thoughts on it. So if anyone has any questions, just feel free to interrupt at any time. Okay, so to start, maybe let me discuss a little bit about what distributed entanglement is and why we care about it. So on a very basic level, distributed entanglement just refers to two distant parties that are physically separated, Alice and Bob. And their goal, or what they would like to have, is they'd like to share some entangled particles between the two of them. And one might ask, like, why do you want to do this? Or why might Alice and Bob want to share some entangled particles? There's a number of applications of this. The first is quantum sensing. So this was proposed by Daniel Gottesman, and this idea of long baseline telescopes using these like entangled bell pairs. So the basic idea is that you have two telescopes that are separated, and they share some bell pairs across the two of them, and you have some signal that's coming in from space. And the idea is that you want to use these two bell pairs, you want to use this bell pair, which is entangled, to basically detect the phase shift in the received signal across the two telescopes, and this gives you some resolution or some information about the source from which the signal came. And the idea is that actually by using entanglement, you can achieve a much better signal-to-noise ratio than you can compared to using classic like optical telescopes. So this is one case where distributed entanglement might be useful. Another is for secure communication. So sharing bell pairs is kind of the basic substrates for a lot of like quantum key distribution schemes. Another one is networked computation. So the figure on the bottom essentially shows like a simple quantum state teleportation circuit. And the basic kind of, you could say, catalyst that's necessary for this teleportation circuit to work is that it requires consuming one bell pair every time you want to teleport one bit or one qubit of a quantum state. This is particularly important, especially in the case of like early to near-term quantum computers, which we believe will have maybe on the order of thousands or tens of thousands of physical qubits. So it could be the case that one single error-corrected device just doesn't have enough qubits to do an interesting computation, and you'll need to network or connect together a bunch of these different processors together in order to do one larger computation, in which case you'll need to share high-fidelity entanglement across these two networks to essentially form a nice coherent channel to allow you to form what is essentially a larger quantum computer. So essentially the basic theme across each of these three applications is that they require distant parties to share high fidelity entanglement between the two of them. So how do we actually achieve this? The problem is that real life quantum channels are noisy. So a very basic method that you could consider to like achieve this goal of having high fidelity entanglement across Alice and Bob is that Alice prepares these entangled particles on some local quantum processor, which we will assume for now is actually noiseless, which is quite an optimistic assumption. But for now, let's assume that she can perfectly prepare these entangled particles just on her side. And then she takes half of these entangled particles and sends them across some quantum channel to Bob. And if this quantum channel were perfect, then Bob would just receive these entangled particles, and then the two of them would be good to go. The problem is that these channels in real life are often quite noisy. So errors can occur in this channel, losses, all sorts of crazy things can happen. And Bob might not receive the perfect version of the entangled pair that Alice wanted to create. So what can we do? Well, this is kind of what entanglement distillation as a problem was initiated to study. The idea is that Alice will send over many, many copies of some entangled particle to Bob. And the two of them will kind of work together in order to distill out a few copies of very, very high entanglement or very, very high fidelity entangled particles using some combination of local operations and classical communication. So this means that you can imagine that Alice sends over, say, 20 bell pairs across some noisy channel to Bob. And when they get to Bob, they've been corrupted in some small way. But through a combination of just local operations, meaning some local unitaries on Alice and Bob's side, and classical communication, meaning Alice and Bob are allowed to talk, but only over a classical channel, they're able to distill out, let's say, 10 bell pairs, which are nearly perfect. So this is kind of the goal of entanglement distillation. Is the task clear? Are there any questions so far? Good. Okay. So to get a little bit more formal, let's kind of try to give a mathematical formulation of the problem. So let's say you are given n bell pairs, each of them with some infidelity epsilon, which you can think of as essentially an error rate of the channel. The goal is to increase the fidelity of the bell pairs as high as possible using the fewest number of resources. Quantitatively, what this means by increase the fidelity means you typically want the output error rate with this bar epsilon to be below some fixed reference value, which is typically taken to be very small. So depending on the application, you might see a range from anywhere between 10 to the minus 6 to 10 to the minus 12. So very, very small output error rates. And the resource quantification is essentially the overhead, meaning the number of input bell pairs you need to consume in order to produce one clean output bell pair. So quantitatively, this is just n over k. And you want this number to be as small as possible because you want to be kind of frugal with how you consume your input bell pairs. And you want to produce as many output bell pairs as possible, given what you've got. So mathematically, it's really just you're minimizing overhead such that this bar epsilon is less than some reference value p. So I want to note now this kind of interesting connection between distillation and error correction. So this connection was actually noted in the seminal paper that even introduced the task of entanglement distillation from Charlie Bennett in 1996, where him and his co-authors kind of realized that entanglement distillation can be thought of as correcting errors over space, whereas error correction in the classical or like in the typical sense can be thought of as correcting errors that occur over time. So this connection can actually be made formal and a little more rigorous than just like this nice diagram that I've drawn, meaning that most protocols for error correction can be turned into protocols for distillation and vice versa. And we'll actually be taking advantage of this kind of nice connection or duality in this talk. Okay, so to kind of break down the main ideas in our work, there were really two ingredients that went into designing these protocols that can achieve a constant overhead entanglement distillation. The first is actually using error detection. What error detection is essentially, rather than doing error correction, where you kind of try to figure out what the error is and fix it, error detection is a slightly easier task where you just try to figure out whether or not there was an error. And if you figure out that there was an error, then you simply discard the whole thing and start over, which can be quite wasteful, but also the conceptual simplicity actually leads to some wins, which we'll see down the line. So to actually discuss how the error detection works, the first main kind of mathematical tool that we need is this Choi isomorphism. When one observes that there's these four canonical types or four canonical entangled states. The first one is the bell pair that we all know and love. And then there's kind of these different versions of the bell pair with different phases attached to them or different bit flips. So you have this psi z, which is essentially a bell pair, except for you have this minus sign over here, this psi x, where you have a basically a bit flip, and psi y. So these four bell pairs, or these four kind of canonical entangled particles, are actually associated in a one-to-one fashion with the Pauli matrices. And the easiest way you can see this is if you actually just wrote out the state vectors for each of these. You get a length 4 vector, and if you just move the bottom two entries over to get a 2x2 matrix, then you would basically get the Pauli matrices. And we're going to be making use of this isomorphism over and over again. The next kind of fact that you can observe is that you can actually write any input entangled state as, or no, this is not true. You can, what I'll say is that you can assume that your input state is a linear combination of these canonical entangled states. This is not always true in general. So why is this kind of not too restrictive an assumption? It's because given any input state, you can always turn it or transform it into a state of this form by essentially applying random Paulis on both ends. If this idea isn't familiar with you, if you're familiar with error correction, this might be a little bit more obvious because in error correction, you kind of, it's generally taken as an assumption that you can ignore coherent errors and just assume all your errors are Pauli errors. This is pretty much the exact same idea. The idea being that like when you do your syndrome measurements or when you do any sort of operations, you always end up projecting back down into a Pauli error anyways. So it's a safe assumption that you can just pretend your errors are always Pauli. And that's really what this equation is saying. You can just pretend that your noisy quantum channel is always applying some form of Pauli error. And the final trick that's needed for this like error detection idea to work is this identity, which says that if you apply U tensor U star, where U star is just a complex conjugate of U on one of these like reference entangled states, you just get a transformed version of the state where you replace the Pauli with like U dagger PU. So rather than writing that in equation form, I think it's easier to visualize it. So you can imagine your input state with some error P applied on it, your input bell pair with some error P applied on it. You can draw it in a tensor network fashion like this. When you apply U tensor U star, so Alice applies U and Bob applies U star, this turns out to be exactly equivalent to just U dagger PU being applied on Alice side. So visually, you can just imagine sliding P up and then sliding U star up. And when U star goes up, it basically turns into a U dagger because you pick up a transpose when you slide U up. So this is just known as the transpose trick. And what this buys you is that you can essentially think of applying U tensor U star as transforming your Pauli error in some way. So we'll make use of that for our error detection component. Okay, so the basic setup of error detection is as follows. Alice and Bob both receive n noisy bell pairs, or like Alice receives half of n noisy bell pairs and Bob receives the other half. Alice applies U, Bob applies U star. I should note that U star is fairly easy to derive if you have some like circuit representation of U that's like say decomposed into Clifford plus T or something like that. Any sort of decomposition you care to consider. You just replace any gate that has like an imaginary component, like for instance, an S gate, you replace it with S dagger because that's just a complex conjugate of S. And purely real gates like Hadamard gates, you just leave as is. So once you know U, it's pretty easy to derive what U star is. And then after Alice and Bob are both done applying their unitaries, they both measure their halves of just K pairs, or that should actually be an M. So they both measure some of their bell pairs. And then they compare the outcomes, basically. And what they do is that if the measurements actually disagree, then they discard and repeat. And if they agree, then they just continue and accept, and then conclude that no error occurred. So why is this the case? Well, you can see why by just looking at the 4 kind of bell pairs or 4 entangled states that you derive from the Choi isomorphism. So 2 of these bell pairs corresponding to X and Y, you'll see that if you measure both of them in the computational basis, the measurements will always disagree. Whereas for psi I and psi Z, the measurements will always agree. So basically this test where you're checking if the measurements agree or disagree amounts to checking whether or not there was an X or a Y error on your input bell pairs. So actually just building off of this simple idea, you can derive a pretty simple protocol for entanglement distillation that actually lets you get the fidelity of your output bell pairs arbitrarily high. So it does turn out that the cost of this protocol is very high in terms of the overhead, but it does work in the sense that you can get your errors to be arbitrarily suppressed. So you might be asking, like, what happens to the Z errors? Because it looks like the Z errors just pass through the test with no problems. You can easily take these into account by just applying a Hadamard before, and that'll transform your Z into an X error, and then you apply the test, and you'll catch the Z error, basically. So if you do that, then it actually turns out that you won't catch the X error because the X error will be transformed to a Z. But you can kind of fix this by just iterating your test over and over and over again. And then basically 1 round you're catching X errors, 1 round you're catching Z errors, and so on and so forth. So this is actually the idea that was proposed in this seminal paper that I brought up that made this connection between error correction and entanglement distillation. And they have this nice figure in their paper where they're able to show that the output fidelity, F prime, is actually higher than the input fidelity using this test for some range of fidelities. I think it's actually just once it's higher than 0.5, you're always getting better and better bell pairs. So you can just imagine basically iterating this test and you kind of bounce up this curve and get arbitrarily close to a fidelity of 1. Okay, so to maybe zoom out a little bit, what are the desiderata that you might want from any sort of error detection based protocol? Well, you want a test on your input bell pairs that's 1, computationally efficient, because you actually want to run this thing in practice. So you should be able to kind of process the information and run these unitaries in like at least some polynomial depth. B, you want it to be very, very sensitive to input errors. So that way you can basically catch anything that went wrong with the input bell pairs. And C, you actually want it to have a fairly reasonable rejection rate. So you don't want to be throwing out the inputs too often, and you don't want, because this kind of leads to waste. And the way that you can see this is that you can write the expected overhead of any error detection based protocol as this factor n over k, so n being the number of input bell pairs divided by k, the number of output bell pairs, with this additional factor that scales inversely in the failure probability, because this basically measures the number of times on average that you'll need to repeat your error detection test before you conclude like you've succeeded and you just allow it to pass. So if either one of these numbers is too large, then the overhead of your protocol will just be not friendly. And actually, there is a kind of trade-off between these two numbers that I'll discuss in future slides. But the basic idea is that you can actually make either one of these very small pretty easily. So you can make n over k pretty small by just essentially setting k to be equal to like n minus 1 or something. So every single time you only discard 1 bell pair. The problem is that this makes the output fidelity not grow too quickly. You can also make the failure probability pretty small by basically making your test not stringent enough. So both of these things kind of have to be carefully controlled and weighed off against each other.
Sorry, can I just ask a question? Just
yes, yeah.
A basic clarification question. If you measure the bell pairs, then you destroy them, right? So what am I missing?
Yes, that's right. So basically the idea, let me try to forward to, okay. So the idea is actually you get like n bell pairs and then you only measure some of them. So you basically destroy the ones that you measure and then you keep the remaining ones, if that makes sense. So the goal here is actually just to measure as few bell pairs as possible, because like you said, once you measure them, they're destroyed and you can't use them for anything else. The only ones that are actually useful for the future are the ones that you haven't measured. So that's why it's important that you're given like n bell pairs. If you're only given one bell pair at a time, then you can't do much, right? Like if I just give you one bell pair and I tell you I want you to do some distillation on it, there's not much that you can do. I need to give you, say, like 30 bell pairs at once, and then you do some joint operation on the 30 bell pairs, and then maybe output 20. Does that make sense?
Oh, well, okay. So I thought you were measuring one bell pair at a time. So you're not doing that. You're doing like a, yeah. Can you explain what's going on here? Because I mean, it seems like obviously if you do one bell pair at a time, you detect the error or don't detect the error for a particular bell pair, but then you've just ruined that resource and you
Yes.
change nothing about the rest of the bell pairs, right? So you're trying to do some joint thing. Like if you have
Yes.
20 halves of a bell pair, you want to measure 10 of them, and then like, but in some joint way where you measure all 20, but
Exactly. Exactly.
yeah,
Yes.
only destroy
So
10.
you basically,
So how does that work?
the idea is you take your 20 bell pairs and you apply some big joint unitary on all 20 qubits on either side. Like both Alice and Bob apply some big joint unitary on their 20 bits and their 20 qubits. And then you do some measurement on 10 qubits, which is equivalent to doing some sort of crazy entangled measurement on the initial 20 qubits of each half. So if you prefer to think of it that way, you can also think of it as like some big entangled measurement, which destroys some of the bell pairs, but leaves some of the other ones intact. And you're kind of trying to choose the right subspace that you're doing this like entangled measurement in to get some information about everyone, like in the sense that like you're trying to detect some error anywhere without destroying everyone. Does that make sense?
Yeah, that makes sense. I just don't know how that squares with what you were saying earlier. Like, because you're saying like, you do this, you measure a qubit, and then if it matches, Alice and Bob match, then you've gotten rid of the X and Y errors. But actually the picture is
I
like this
see.
complicated joint measurement. So how do those two things square?
Yes. So I was kind of cheating a little bit here. So you wouldn't actually. So yeah, I give you a bell pair, and then you wouldn't actually just measure that bell pair, and then if the measurements disagree, then you're like, okay, there was an X error on the bell pair, but now the bell pair is gone, so who cares? What Charlie Bennett proposed is basically you're given two bell pairs, and then you do a C naught between the two of them. And then basically the idea is that the C naught will spread an X error from one of them onto the other one, and then you measure that other one. And if that other one has like this disagreement, then you kind of infer, roughly speaking, that the original bell pair had an X error. That makes sense. So it's actually a very similar idea to like error correction, where you're using some entangled gate to spread an error from one onto another.
Yeah.
You do the measurement there, you learn there was an error on the other one without destroying the other one.
Yeah, I was actually kind of surprised you just didn't describe it that way. Because I roughly remember from that paper, it's like, yeah, you have two bell pairs, you do this C naught and conditioned on some outcome, then you'll know when to keep the remaining qubits, something like that.
Yes, yeah, I was trying to cheat a little bit, but yeah, that probably would have been clear. Yeah. Yeah, so I hope that clarifies. Cool. Okay, and the second ingredient here is random codes. So the idea of random codes extends back a very long time. I think the first time they were proposed was with like when Claude Shannon basically invented information theory. He essentially showed that random linear codes achieve channel capacity. What that means is like if you have some message in the form of like bits that you just want to send over some classical channel, if you say this, like if you imagine this classical channel to be noisy and like it's going to corrupt your message in some way, then it turns out that you can essentially use these like random linear codes, which means when you take your input, you apply some random binary matrix to it to, yeah, basically transform the message in some way and then pass it through the channel. At the output, information theoretically, you this is kind of the optimal thing to do in the sense that like you can squeeze the most amount of information into the fewest bit, into like the shortest possible message. So in a sense that these random linear codes have very nice information theoretic properties. The trouble with them is that they're like computationally intractable to decode, meaning that at the other end of the channel, I've received some message, but actually there's no efficient protocol in general to actually recover what the intended message that like Alice wanted to send was. So this fact that these like random linear codes are intractable to decode is actually the basis for a lot of like cryptographic schemes. So it actually forms like a fundamental assumption for a fundamental hardness assumption for a lot of like cryptographic schemes, which is pretty unfortunate, right? Like you'd like to be able to use the fact that these random linear codes are so good, but in practice it turns out that you just can't because you can't decode them. This is what leads to the idea of just simply combining the two. So rather than actually trying to decode, to decode a random code, maybe you can just use it for error detection. So you can just use this code to detect if an error happened or didn't happen. If you conclude an error did happen, rather than trying to decode it, you just throw the whole thing out and you start over. And this basically circumvents or shortcuts out the decoding problem entirely. So how do you actually generalize that to the quantum case? The idea is that, let's say you're given n bell pairs with any Pauli error that's a non-identity Pauli error. So like, let's say there's like a low weight Pauli error on like a X error on one of the bell pairs. You apply just a random sort of unitary formula. You can think of it as like a random Clifford, but it actually only needs to be just drawn from a unitary 2 design, which is like an even weaker condition than being a random Clifford. You apply C star on Alice and Bob. And then what this does is this twirls or like transforms this Pauli error into this big, huge global Pauli error, right? So this is this picture of like C tensor C star on some psi P turning into like psi C dagger PC. Then it turns out, right, that if you picked C to be a random Clifford or from some unitary 2 design, then C dagger PC is just like a random Pauli, pretty much. So it has this huge weight and it's spread out all over the place. And then what you can do is you can just measure m qubits and then you can basically infer whether or not there was a Pauli error on the input. Why is this the case? Well, basically, if I hand you like a uniformly randomly sampled Pauli, and I just tell you to look at any m of the characters on this Pauli, then with very high probability, you're going to see at least one X or Y at some position. And the probability of this not happening is like basically 2 to the minus m. So it's like exponentially suppressed in how many qubits you look at. So if you make m large enough, then you'll essentially be able to tell for sure whether or not there was an error at the input or not. And that's what this picture is depicting. Like you form this syndrome from calculating the discrepancy between the measurement outcomes, and then S tells you whether or not there was an error. Does this basic scheme make sense? It's really just error detection, except for you're replacing the U with a very specific unitary, which is just a random Clifford or a random 2 design.
So you pick the 2 design uniformly at random?
Uniformly, yeah, just uniformly at random.
Okay. Because there's no advantage if you do it non-uniformly, or
there could be, but basically the idea behind this, as well as random linear codes, is that there's next to no advantage. Like basically by choosing a random one, you're getting very, very good performance already. So you can just do the lazy thing and pick a random one. It's possible that there exists some very special unitary that will like achieve better than random. But yeah, random is oftentimes good enough. Okay, so what's the actual kind of performance of this protocol? Like how high are you able to amplify the fidelity with just one go? So what this is on the left is 1 minus bar epsilon to the k is essentially the fidelity of the output. And you have this, it's lower bounded by this value. So it's 1 minus, and then you can think of this as like the output error rate. And you can see that essentially you can prove that the output error rate is exponentially suppressed in M, the number of measured qubits. And here I've actually included a figure just for you to kind of visualize what's going on. So I've set the input error rate at, I think, 20%. And then what I'm doing is I'm slowly increasing N, and I'm varying the ratio M to N here. So as you go from left to right, I'm measuring more and more and more qubits. The y-axis is the output infidelity. So you can see that it's just strictly decreasing. So the more you measure, the better your output infidelity is, until you get to this kind of critical value, at which point it essentially flattens out to zero. So there's this interesting phase transition. And this line basically turns out to be, it's pretty simple to show. It sits at the log of the input infidelity. So this is like log of 0.2. Yeah. So what I hope this illustrates is that with random codes, you have this test on input bell pairs that's pretty computationally efficient, because all you have to do is apply this random element of a 2 design. These things are very efficient to realize in practice. There's constructions that do these things in logarithmic depth. So very nice. It's also very sensitive to errors. As you can see from this figure, it's getting suppressed very rapidly past this critical point. And also mathematically, it's just exponential suppression in M. And the final thing is that it has a fairly, the final question is whether or not this thing has a reasonable rejection rate. And it actually turns out that the bad news is this test is very, very strict. So you can actually bound the acceptance probability between these two values. So f to the n, and then f to the n plus this exponential correction, this exponentially small correction. The question is, what is this f to the n? Well, this f to the n is the probability of all n inputs being perfect in the first place. So the moment you start working with like large n, say 100, 200, this is pretty much zero. So like your acceptance probability is going to vanish very, very quickly, and then your overhead is going to balloon. So this is the real problem, right? Like we've essentially invested too much in achieving a good fidelity improvement at the cost of a very, very high rejection probability. But the good news here is that we have complete freedom in how we choose n and m. So n being the number of inputs and m being the number of measured bell pairs, or bell pairs we throw away, basically. And it turns out that by very carefully balancing n and m, you can actually kind of balance these two factors of rejection probability and fidelity improvement. I'm going to discuss that right now. The basic idea is just concatenated error detection. So put very simply, you just want to be gentle kind of in how you're doing your error detection. You want to very slowly increase the fidelity of your bell pairs rather than trying to take it from like error rate 10% to error rate 10 to the minus 12 all in one shot. You want to kind of improve it from 10% to maybe 5% and 5% to 2% and slowly work your way towards 10 to the minus 12. So how do we do this? Well, you start with a very small n and m. So at small n and m, everything is kind of nice. You have a reasonable failure probability, but at the same time, you can't suppress your errors that much, but you can still suppress them. So you get some small wins. And then you run your random Clifford test, which gets this like reasonable amount of suppression. And then you just increase n and m, basically. So you take the outputs of these small Clifford tests, and then you run a larger Clifford test on it. You amplify the fidelity a little more. You kind of increase n and m again, and you rinse and repeat. And then at the very end, hopefully you have these like very high fidelity bell pairs, and you haven't thrown out too many along the way. Yeah, so rinse and repeat. Okay, so the kind of key mathematical result of our paper is essentially this lemma and the next theorem, which I'm about to present. For the lemma, which we take use of, which is kind of, you can think of as forming each layer of our concatenated error detection setup, is that given some input error rate epsilon, you can use our protocol using the specific parameters listed below to get an error rate which is essentially exponentially suppressed, an exponentially suppressed function of the input error rate. So what that actually looks like, I plotted this blue line is just no suppression, so y equals x. And this red line is 2 to the minus this function over here. So you can see that below this critical input error rate, you can get very, very rapid suppression. And if you just iterate this map a couple times, you can basically get as low as you like pretty quickly with very few iterations because it's exponential suppression. I've listed some of the parameters here just in case it might be of interest. It turns out that if you just choose the number of inputs to be 1 over square root the error rate, and m being 1 over cube root the input error rate, then this is kind of the performance that you can expect. I want to note also importantly, the acceptance probability is asymptotically equal to 1. So it's basically 1 minus the square root of the input error rate. So as your input error rates gets smaller and smaller and smaller, your acceptance probability just tends towards 1. So you've kind of solved this problem of having a rejection rate that's just crazy, while at the same time getting very nice and rapid error suppression. So if you guys are kind of attentive, you might notice that actually above this critical point, the errors actually tend to get amplified. So I'm going to discuss that. This is kind of more of an artifact of like the fact that we wanted to write down a theorem. In practice, these might not actually be the numbers that you use. Yeah, so this is purely for theoretical purposes. It's like at some point you can get this exponential suppression. So the theorem essentially says that if I give you input bell pairs with any infidelity that's like better than 0.5 and any target infidelity, so you can choose anything that's positive. It can be 10 to the minus 12. It can be 10 to the minus 1,000, whatever you like. Then this like concatenated protocol succeeds with an overhead that's completely independent of your target infidelity. It does depend on some like failure probability. So basically you can say I'm going to allow my whole protocol to like fail with some probability 10 to the minus 15 or something. And when my protocol fails, it will tell you I failed. Like it will output some fiducial state which says this protocol did not work. You need to start over from the top. But the important thing is that the overhead is like independent of the output infidelity. And there's some other parameters which I've listed here for completeness. Basically, the amount of memory that Alice and Bob require is polylogarithmic in the target infidelity. The number of layers of concatenation is essentially constant, so it's equal to like asymptotically equal to the iterated logarithm of the target infidelity. And also the gate count is pretty favorable, so it scales polylogarithmically in the target infidelity. To show some concrete numbers, you can actually numerically optimize the various parameters of the protocol, N and M, and also do this concatenation in various ways to basically try to achieve as small of an overhead as possible. So what this figure is showing is the x-axis is the input error rate. The y-axis is the expected overhead. And I'm showing how, like, what the expected overhead is to reach an infidelity of 10 to the minus 12, which is kind of this typical number that people will quote for like, what error rates do you need to achieve to get like networked computation working well? So you can see that for L equals 0, 1, and 2, these are the values from our work. You have pretty favorable overheads, even for like fairly large input error rates. And just for comparison, we've listed 2 other previous works that were like doing entanglement distillation and were like, to the best of our knowledge, like the state of the art. So with just 1 or 2 layers of concatenation, you can get really, really good overheads for most like reasonable regimes. Okay, cool. I just want to stop here and check if there's any questions so far, if the protocol is clear and if the theorem makes sense. Okay, awesome. So in the time that we have remaining, I want to quickly go over some like kind of an interesting idea. I want to talk about basically considering a return to maybe error correction. So like talk so far has been very focused on error detection. And the question is like whether or not this is wasteful at all. So right now we basically throw away any realizations of our test for which the measurement outcomes disagree. And the question is whether or not we're being wasteful. Like, can you do better than just being lazy and throwing out any measurements which disagree. I'll kind of argue that you can. The idea is that the map from input error to syndrome is a many-to-one map. So many different pallies will result in the same syndrome. But not every single P is equally likely. So although this like map is not really invertible, if it was invertible, then you would be golden. You could kind of just take your syndrome, infer what error happened on the channel, and then just fix it. But it's not, it's a many-to-one map. So the best you can do is kind of try in a statistical sense to infer what's the most likely P to have occurred. And the way you can do this is by kind of imagining just building some sort of lookup table. Like you can imagine, okay, I have some syndrome here, which is like all zero syndrome, meaning every single measurement disagrees. What are the errors on the channel which are compatible with this syndrome? Well, there's obviously the identity, meaning like no error. And then there's some other errors that you can consider. The same goes for this other syndrome, which I just made up. Maybe that's compatible with a single qubit X error. And then a whole bunch of other things. So you can repeat this exercise for every single syndrome if you just imagine you had like unlimited compute. But what you can realize is that within each of these sets, most of these errors are very high weight, and there's just one error which is like the lowest weight error out of everything in the set, and this is the most likely one to have occurred. So if you observe this syndrome, then you'd be justified in saying or inferring that this was the error that occurred, and you'd be wrong some of the times, but those would be kind of very, very suppressed compared to most of the times. So what you can do is you can build this using this like lookup table idea. You can build a large but like finite lookup table. So you can try to correct up to capital E errors. So you can fix this number at whatever you like. I think for the purposes of our work, we chose 10 to the 7, which is a very reasonable, basically dictionary size to maintain on like modern computer hardware. And the idea is that if a syndrome hits, meaning if you observe some syndrome that exists in your lookup table, then you simply apply the correction that your lookup table recommends, meaning like the lowest weight error. If not, if it doesn't exist in your lookup table, then there's nothing you can do. Then you basically just throw the whole thing out and start over. So this should lead to a strict improvement because the original version of our protocol is essentially one where our lookup table is just size 1. The only row in our lookup table is just the all zero syndrome, and then we accept if we see that, and otherwise you just throw the whole thing out. So this is kind of a strictly more general version of our protocol. And you would expect the performance to improve, and as a matter of fact, you actually do see it improve. The overhead shrinks by almost 2 orders, I think closer to 1 order of magnitude in some cases. And the improvement is kind of most noticeable for like the non-concatenated version of the protocol where L is 0, so you don't concatenate at all. But even for the concatenated versions, you can see kind of a fairly substantial improvement by up to like 3 or 4 factors. Cool. So just to summarize here, what are the wins of our protocol? Like, where does it really shine? The first is that it achieves asymptotically constant overhead independent of the target output infidelity. This is a really nice theoretical property that's kind of just intellectually satisfying, I guess. The main technical tool that we use to achieve this is the fact that random codes have very favorable performance in the sense that it's quite sensitive to noise. The second, out of theory land, is that it achieves fairly favorable practical performance in 2 respects. The first is that by taking advantage of like the exact closed form for all of the parameters and like output infidelities, it means it's very easy to optimize the hyperparameters of our protocol numerically. The hyperparameters being like n, m, and the number of layers of concatenation. These things are all fairly easy to like optimize. The second is that in terms of like practical implementation, these 2 designs which we require can be implemented in logarithmic depth. So the depth of the circuits required to do this protocol are fairly shallow. And the final thing is that I would say it's fairly amenable to extensions. So as I demonstrated in the last couple of slides, it's compatible with some limited amount of error correction rather than error detection. And there's also possibilities of like further constraining the depth, which I didn't talk too much about today. And just to leave some food for thought for future work. There were kind of two interesting questions that we were left with. The first is whether or not two designs really are strictly necessary, because the only reason we required two designs is that we wanted to scramble up these like small local errors into huge global errors so that they could be very easily detected. And it seems like the critical property here is like scrambling rather than two designedness. So the question is whether or not using some sort of analog systems or basically any sort of like Hamiltonian or any sort of evolution, which is generically scrambling, does that actually suffice? And can you prove anything about that setting? And the other question that we have is that mostly, like throughout most of this work, we assumed no local noise on Alice or Bob's side. We assumed that all of the noise sits on the channel between Alice and Bob. And the question is like, how well can you adapt this protocol to work in the presence of local noise? Yeah, so with that, I'm happy to take any questions. I hope you guys took something away from this talk.
Okay, thank you very much for a splendid talk with some very nice, interesting results. Yeah, so if people have questions, please feel free to unmute and ask them right now. We have, quite some time. Okay, maybe I can go first. So, like, because you showed us like how it performs with different layers, like of concatenation, right? Like, but so this is like you have to sort of try increasing the number of layers. Like it doesn't immediately tell you what would be sort of like the optimal choice, how much concatenation.
Yeah, that's a great question. That's true. We didn't actually explore like if there's a way to determine and like a principled way of determining what's the exact optimal. My intuition is that basically you could just continue improving, like you could always get better by just increasing the number of layers of concatenation. You would just get increasingly small returns, basically. Like you would get diminishing returns to the point where like it looks like this green curve is already as good as it's going to get. Like going from one layer to two layers is really not changing things all that much. Maybe a theoretical way of seeing this is that in our theorem, like to achieve this like constant overhead, what we require is the number of layers of concatenation is like the iterated logarithm of the output infidelity. And an iterated logarithm is essentially constant. Like you could choose an output infidelity of 10 to the minus like 1000. And the number of layers of concatenation recommended by the theorem would be maybe like 5 or 6 or something like that. So yeah, my intuition is that like you're not really getting much improvement past 3 or 4 layers of concatenation, although you would see some small finite improvements.
I see. And maybe like one quick question. So as you mentioned earlier, there's a connection between sort of like distillation and error correction. So when you concatenate here, so there's an equivalent concatenated code for it. Is that right?
Let me think about that. Yes, there would be. The equivalent concatenated code, it would be like if you looked at a particular instantiation of this like concatenation, basically the code would be defined by like the inner code is like whatever random Clifford you chose for the green blocks. The outer code would be whatever random Clifford you chose for the blue blocks, and then maybe the outermost code would be the purple one. Yeah, so I mean the duality is usually like it runs pretty deep in the sense that like pretty much any version of distillation you can come up with, there's an analog in the error correction setting. Yeah, that's a great question though.
So in terms of error correction parameters, what are those N, M, and D, NK and D? Do you
NK and D? Oh,
like if we speak of like the error correction language, right? So
sure.
Is this a good code? So when I say
these
good
are
code,
asymptotically good codes. Yes.
Oh, I see. Okay.
So the codes formed by random Cliffords are known to be asymptotically good in the sense that K and D are both theta n. The problem is that people don't like using them for error correction for a number of reasons. The first one, and probably the most significant one, is that you just can't decode them. So there's no way of like, you can't really saturate these parameters in practice because you have no way of decoding it. So you can't really achieve the linear distance.
And in your in your example, decoding isn't a significant issue because you use table lookup, is it?
Yeah, so my example here, this is actually not full error correction, precisely because I allow for this possibility of like, if my syndrome doesn't exist in my lookup table, then I reserve the right to just throw everything out and start over.
Okay.
Which isn't really the case in error correction, right? Like you don't really want, you don't want like halfway through your computation to just get some syndrome and be like, okay, well, it's not compatible with my decoder. I'm going to throw my whole computation out and start over. But you can kind of do that in this setting because restarts are cheap. Yeah, so this is not really a full decoder. It's like a partial lookup decoder. You can think of it.
Okay, thank you.
I just wanted to ask, so I guess there's a connection between these like entanglement distillation, the theory of entanglement distillation and the theory of like magic state distillation or something like this. And so if you wanted to like take whatever you built here and apply it into magic state distillation world, have you thought about that and what do you get in that world, or is it already known in that space?
That's a great question. So that actually was kind of the natural follow-up that my collaborators and I were thinking of once we'd finished this. We kind of hit a dead end for kind of interesting reasons. It'd be the easiest way for me to summarize like why we hit a dead end was because the main kind of one of the main reasons this works is because of this just because of this identity where you have like C tensor C star on psi p being this. And the important fact here being that C tensor C star on a perfect bell pair leaves the bell pair invariant. So you basically discovered this whole class of unitaries very easily, which leaves your like target output state untouched. For magic state distillation, the equivalent would be like, can I find some unitary that leaves my T state invariant, right? Or my CCZ state invariant, which in the language of error correction is like, can I find codes with transversal T's? That makes sense. Which is already basically the hardest step of the problem. So something that's like very easy to take for granted in the bell pair setting where you have this nice, pleasant identity, just does not translate over whatsoever to the magic state distillation case. Where there, like the whole project is to discover a class of unitaries that leaves my T state invariant. Yeah, does that make sense?
Yeah, kind of, I think. So what's wrong with like, all diagonal, like all like I's and Z's, along with permutations or?
Yes. So that's true. You can always write down some class of unitaries that leaves your T invariant. The problem is that those ones, if you just choose the kind of obvious ones in the sense that they commute with your T, like they're all diagonal or something, they're just not going to catch any X errors. Or which errors won't they catch? They won't catch the Z errors because they commute with Z errors as well. Yeah, let me think. Yeah, they won't catch the Z errors. So you need to come up with like a broader class that's not just trivial in the sense that it's like they're diagonal, so it works. You come up with like off diagonal unitaries that still commute. And then it gets a little bit more complicated. There's a question of like whether or not you can bootstrap existing known codes that have transversal T's and then like try to apply some of these ideas. We didn't really kind of go down that route we were trying just on our own to kind of come up with classes of unitaries that satisfied this, and found it pretty hard. But yeah, maybe we're taking a wrong approach. I have no idea. Yeah, it's still something we're like actively thinking about. So if you have any ideas, that would be very welcome.
Okay, nice. Thank you.